for the purposes of this argument, let's say that this is a large sheet and that it has a surface area of A and that it is charged positive Q. So if we assume it's a very thin sheet, then there are certain things we can bring up about it. You know, sigma is going to be Q over A, stuff like that. We also know that from Gauss's law that it is producing an electric field that points away from the sheet, and the electric field is uniform. I don't throw that word around incidentally. I think you guys tend to think of it as just a flavor word, but it's not. If you say uniform, you are saying it is constant. It is the same value everywhere. So it's important that if the word uniform gets brought up, it relieves a whole bunch of your mathematical restraints, because the moment something is uniform, you don't have to do, there's not going to be a lot of integration or anything like that, because your integrand is going to deal with things that are all constants. So if you get to say the word uniform or you get to hear the word uniform, pay attention. That's a valuable word. It can totally change the nature of what it is you're trying to do. So it's a uniform electric field, meaning it's constant. Now, electric field, as you know from our prior examples, is sigma over 2 epsilon naught. Or if we use the information that's here, it would be Q over 2 epsilon naught times A. Okay, just a reminder of last time. Here's kind of where I made, not kind, this is where I made the mistake. If we take and have a second sheet, and we place it in a similar place, but charge it negative Q, right? Which is what we are doing when we have a capacitor. So we take all the positive charges, you know, from the bottom plate and put it on the top plate, or take all the negative charges from the top plate, put it on the bottom plate, whatever. The bottom plate will create its own electric field, and because it's negatively charged, it will be similar to the electric field produced by the other plate. And if it's the same value of charge but opposite magnitude in between the plates, we get a doubling effect. And that doubling effect would give us a net electric field of Q over epsilon naught A, right? Twice the size of the electric field. Now, yesterday, in trying to demonstrate, and I had a goal yesterday. I don't know that you guys saw it, but I had a goal yesterday, and one of them was to just show that there's a lot of just simple substitutions that could be made to talk about capacitance, charge, electric potential, stuff like that. I mean, and I hoped you saw all that. Once we're dealing with a uniform field, we have things like F equals QE. This doesn't require a uniform field, but it sure is easier to use this if you know the field is uniform. And then there's things like V equals ED. This is something that is the result of finding the potential difference in a uniform electric field. And this was a question brought from Sahana earlier, actually. You know, if you are trying to find a potential difference from one place to another, and you start at the negative plate and you go towards the positive plate, that's got to be an increase in potential, and your answer has to be positive. And if you go from the positive plate to the negative plate, that's got to be a decrease in potential, and your potential has to be negative. And in both those examples, we're really talking about potential difference, right? It's an increase in potential going towards the positive and a decrease in potential going away from the positive, something that we kind of know. The question I was trying to answer before that student, because I don't want to dox her right here in this recording, so rudely left, was that when you're trying to calculate the capacitance, which is what she brought up, the capacitance is, you know, Q over V, and you are trying to find the capacitance by looking at the shape of the electric field produced by a charged piece of metal and calculating the electric potential that's a result of the electric field. It doesn't matter if the electric potential that you calculate is positive or negative. One of the plates of your capacitor is going to be charged positive, and one of the plates of your capacitor is going to be charged negative. It's the fact that there is a potential difference between the plates that matters. And the size of that potential difference that's related to the charge that is there is defining the capacitance. So you don't need to worry about when you calculate the potential difference in that regards, in that instance, whether the potential difference is positive or negative. You just need the magnitude. But the student persisted in not understanding. And all I said is, like, if you work it out and the answer comes out to be negative, then ignore the negative when calculating the capacitance of the device. That's it. That's all you have to do. But they persisted in still asking the question a third time. So I didn't know how else to explain it, but I'm making it clear, I think, to you guys, it doesn't matter. You're trying to find out if you put a potential difference on two pieces of metal and it drives some charge, this is what the capacitance is. We're just working the problem backwards by saying, okay, let's assume there's a Q amount of charge. What electric field does it produce? What potential difference is that? Okay, that's got to be Q over V. Does that make sense? But it's going to be a positive value. You can't get a negative value for the capacitance. You can't put charges in there and lose energy. That's not how it's going to work. So, but anyways, from yesterday, it was the idea of putting these pieces out there together. You know, Q equals CV, just solving the capacitance problem from a different angle. U equals 1 half CV squared. You know, we're putting these things out there because they are infinitely malleable as long as you're dealing with a uniform field. And even in some circumstances, if the field isn't uniform. You know, and then finally we also had this, which we proved another way. But the thing that I want to emphasize is all of these things are interrelated. Right? They were all internally proven by each other. Right? So we use this to figure out this. Right? Ultimately, that's what happened. And we used this to figure out this. And then from there, we used this and this to figure out that. I mean, these are all interrelated. So in trying to figure out, A, what is the force on one plate from the other? We did a manipulation and made a mistake. I made a mistake. And reason I'm being slow and diplomatic is because a lot of times I'm speed running through this, I feel. And the people who are understanding are just doing the same thing they always do, nodding their head like a bobblehead doll, like, yeah, that makes sense, yeah, that makes sense, yeah, that makes sense. Then they walk out the room and they're like, what did he say? And then the people who have no idea what's going on. You know, they're just like, oh, whatever he says must be true. I don't know. I don't even know what we're doing right now. Okay, so here's what we were doing. We're trying to figure out the force on this plate from this plate. We know they are attracted together. They are of opposite charge. And I said we probably could start with F equals QE. All right, that's where we started. Okay, well, how do we figure out what that force is? Well, over here on the left, there's probably a way we could express the electric field in terms of something we already had, which was the potential difference. We applied a potential difference between the plates. If you'll recall, I used a symbol. I said we are applying a potential difference, and I used the script E that represents the EMF to try and differentiate it from potential difference, and V for voltage. So here's where the mistake was made, that I made. The electric field between the plates, as it stands right now, is this. Because it's a combination of the electric field from both plates. However, the force on one plate from the other can only come from the electric field of one plate, meaning this plate experiences a force from the electric field only from this plate. The top plate is producing, let's color code this for those of you who would like some color coding, and for those of you who are colorblind, bummer. So I'll use red and green, because anybody who's colorblind, red-green, which is probably the boys in the room, it's just gray and gray, so good for you guys. But one of those grays is green and one of those grays is red. So look, the red arrows, which I circled in green, the red arrows represent the electric field from the bottom plate. The green arrows represent the electric field from the top plate. The electric field from the top plate can't cause a force on the top plate, right? You can't push yourself, is kind of what it comes down to. And the red, the electric field from the bottom plate can't cause a force on the bottom plate. So the only way the top plate experiences a force from the bottom plate is from the electric field from the bottom plate, which means, although we can use electric field equals V over D, we can use that as the size of the electric field between the plates. This electric field is the entire electric field because it is caused by charging two plates. That's where the potential difference came from, us moving the charges from one plate to the other. So in our derivation of the size of this force, we had to divide this in half to only be the electric field from one of the plates, which when we substitute in would give us Q epsilon over 2D. Now that is the force. And if we were to take that force now to do the work and do our integration, we would be okay. Now to do that, we would have to get an expression for Q, which is also what we did, right? We got an expression for Q and subbed it in. And that involved us using this and this. That's what we did yesterday. If you do that and then integrate, you will find the appropriate change in energy. So, and obviously it will. If you look, we've introduced a 2 in the denominator. And we had twice as much energy when we did this derivation yesterday than we should have had. And it comes down to that. So I don't want to do all of it, but I want to remind you of a couple of things that we did yesterday to get to that point. If we wanted to find the work and do it, we had two different ways we could do it. One way was to find the change in potential energy, which was taking the plates, remember, and we're going to take the plates as they are and pull them apart a distance 2D. So this was going to be U at 2D minus U at D, right? And that's what we did for one way to find the work. And the other way to find the work was to actually integrate f dot dx from D to 2D. This is what we were doing yesterday. Now, for the delta U, which is the easier way to do this, we just used 1/2 CV squared, knowing that C for D was going to be epsilon naught A over D, and C for 2D is epsilon naught A over 2D. You guys remember that from yesterday? Okay. So 1/2 C V squared minus 1/2 C V squared. Okay. Now, continuing just this piece of work to get delta U, a lot of that is the same. We talked about that yesterday. So we factor out all the stuff that was the same, and that was 1/2 epsilon naught A over 2D voltage squared. That's the same in both terms. And I just had a 1 minus a 1/2, or no, 1/2 minus 1. Yeah, 1/2 minus 1. Which gave us negative 1/4 epsilon naught A over D. I'm sorry, I factored out the 2D there. I meant to factor out just the D, because that was the part of the term that was the same in both. Epsilon squared. That was calculating delta U directly. Now to do the other side of that problem, to do it by finding the work done, we would need an expression for the force, but I'll remind you the force had Q in it. And we really can't have Q there because as we pull the plates apart, the Q is going to change because the capacitance is going to change. So we needed to use an expression that, quite frankly, didn't have Q in it. But we have an expression we could use. We know that Q equals CV, or in this case, that. Does that make sense? And that this is going to be epsilon naught A over, I'm going to put an X here because our capacitance is going to change as we go from one value of X to another value of X. So I'm putting the X there to represent just whatever the distance is between the plates. This is the part that is changing as we move the plates apart. That force is changing as we integrate. And let's see, putting that in for, that's C, and then we have epsilon. And then our force is going to be Q voltage over 2X. I'm using an X there also to represent the fact that as I move the plates apart, X is changing. It's not a fixed value of D. I wasn't super clear about this yesterday. I want to be super clear about it now. The force isn't constant. When I put these together, all right, Mr. Shelton, do some algebra and do it. Make it look like you know exactly what you're doing. Okay, so epsilon naught A voltage squared over 2X squared. There we go. Just combining it. Please make sure my algebra is right. Because I practiced yesterday, but you know, I don't practice that much. All right, so is there any question about anything we've done there or any mistakes? All right, so we're ready to calculate the work. And I kind of want fewer distractions, which is why I'm kind of moving this onto the screen by itself. Work is going to be the integral from D to 2D ready to go? Dx. Well, I mean, all of this stuff, that's all constants. So I pulled all of those out. And we're integrating from D to 2D, 1 over x squared dx. And now this is x to the negative 2 power. So we'll use the polynomial rule on it. And I know for you guys who are still, you know, banging around in calculus, this won't get easier. You'll just be doing it over and over again. So it'll be habitual. But this is going to be negative x to the negative 1 power, evaluated from D to 2D. Am I going too fast? Irrelevant. All right, that's all the time you get. So this ends up being, if you take the negative sign and absorb it, you can reverse this and just get 1 over D minus 1 over 2D. And this does give us, you know, what we expected as our answer, which is 1 over 2D, which when worked out together, it's going to give us 1/4 epsilon naught A Go ahead, go cool.
I don't understand the context of it. Like, does this mean that when we're pulling apart the plates, it's easier to pull them apart? Like, we're working, since they're oppositely charged, right? Shouldn't it be negative work since we're pulling them apart? But here we get positive work, so that means it's easier, right?
The more we, I mean, you're asking easier or harder, but the more we pushed on the plate, let's go way back to here. The more we push on the plate, X gets bigger and Q gets smaller. Because as X gets bigger, the capacitance of the capacitor is smaller. So it holds less charge. So as we're pushing the plates apart, two things are happening at once. That's why when we actually have an expression for the force gets smaller quicker. It's an inverse square because as we pull the plates apart, we are losing charge and we are losing capacitance. So it was getting easier and easier. Eventually, you just pull them, right? Because they get far enough apart where they're not influencing each other anymore. They're not really a capacitor anymore. Okay? All right. All right. So long story to be able to say that, look, these two things look the same. Right? Grouped a little differently, but one's negative compared to the other because of the definition of how we define potential energy.